Yeah. So we're back. Let's get started on the final exam review. You had a question. Oh, what is? Yeah. So the things I just said were chapters 8 and 9, but that's not going to be on the test. Yeah. I just thought it'd be interesting to see, but it's not covered on that. Final exam review. Woo! I mean, if there are no questions, I can leave right now.
It seems so straightforward.
I mean, we could just awkwardly stare at each other. It was 3.5 years ago. So yeah, we didn't have paper back then.
They just got confused.
Yeah, I wrote it all on the underside of my arm now.
So basically, you took the class 3.5 years ago, and being a TA for 3 years.
3 semesters.
3 semesters.
Yeah. I don't even remember what I put, but it's something like an example of each of the constructions. So like annotated DFA or something, or CFG to PDA, for example. Yeah.
And then I'm assuming examples of recognizable, non-recognizable.
Yeah, that sort of thing. Yeah. It was a different world back then. Yeah. Sure. So, any example CFG in general, or should I just make one up on the spot? Make it up. All right. Using your tuition money well. All right. Okay, so let's say that S is the start variable, like we always do. Well, if I want to convert this thing to a PDA, what should I do? Well, I gotta have a start state no matter what, but what else do I need? Yes, as the construction has, we push the special character on first. So we push the special character on. You can use whatever character you want, $, as long as it's not a variable. As long as it's not a variable, you're fine. And then what do? Then I put the start variable on the stack as well. So epsilon to S. Now what do? Yeah, I look at each of the rules in turn, and what do I do with them? Yeah, make their own branch that does what, though? Yeah, so it looks at each of the rules, but what am I doing on terms of the stack?
You pop the left-hand side,
Mm-hmm.
and then you go from the right to the left and push on.
Correct. So I pop off the left side variable and push the right-hand side of the variable in backwards order so that it's on the top of the stack, right? So then let's see. Let's do the first rule first. So then let's see. What do we got to do? We got to pop S off. Then we got to push C on first because we're doing backwards order. So then we got to not pop C. We got to push C on, then push S. I mess this up all the time. Then I push S on, then I push A on. So it's just popping the variable off, then pushing the right-hand side in reverse order. Cool. So what's next?
After you do all of that,
Yeah, well, let's do the other ones first. So S to B. So if this kind of thing shows up, we're not going to be extremely picky on details in terms of whether you go out or come back or whatever. For these one length right-hand side things, you can just stay at the current state. So you can go out and come back. It doesn't really change the correctness of it because you're effectively doing one transition anyway. So we can actually just stay here for the S to B transition. So we gotta pop S off and then put B on. Say. Yeah, same thing for B to empty, good. So it would be B to empty there. So we took care of that guy. And then what about the B to SA1? Wisconsin, America. Yeah, pop B first, then push what on? Push A on. Should I use the same path that I just made? No. So a lot of people miss points on the second midterm because you reused paths. Make a different one for every rule. Okay? Although, no, that is different, okay. I was gonna say that the self loop kinda is the same transition, but I just remembered they really are different transitions. So we're not reusing anything there. All right, so let's pop B off. Then, so you could push the first character on that first pop transition. It's not necessary, but I kind of like separating the what's being popped versus what's being pushed on, but for correctness reasons, there's no difference. So then we gotta push A on, and then gotta come back, pushing S on. Okay? Correct. Well, as is, does any transition read anything? No, so what do I need to do? Yeah, make it read, and if I read a certain character, what should I do?
Nothing. You just read it.
I read it, and what else do I do?
Oh, pop it out.
Pop it off the stack. Well, where's that transition going to be? A self loop on that third state. Good. And the terminals of this grammar appear to be A and C. So A, push nothing, C, push nothing. Okay, that's good. But does this PDA as is accept anything? No, so what do we need to do? Add a final state. And how do I connect it up to the original machine? Pop off the special symbol. And it doesn't matter whether you push anything or not, but I keep my stack clean. Okay? Does that answer your question? Yeah, so we would need to make the names of the states. So let's call them Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. Is this, if I wanted to, you have a question?
On the final, if you want them labeled, or does it matter?
It doesn't matter unless you need it. If I happen to ask, convert this PDA back to a CFG, you better name them.
Okay.
Yeah. Yeah. Mm-hmm. Yeah, that's perfectly valid too. You could also have epsilon S epsilon, and then push B on coming back. All those are perfectly fine. Yep. So if I wanted to convert this, is this PDA as is ready to convert to a CFG? No. Well, what else do I need to modify? So I'll put a different color.
Oh, the
Single push and pop. Well, what transition violates that? The self loop on epsilon S to B. So the reason why going out and coming, so popping first, then pushing, you guarantee you do exactly want to push or pop on both of them. So on every single one, I mean. So the way to fix that is add a Q9 out here. Looks like a QQ. So then you come out on epsilon, which one was that? It was S, so we pop S off, and then come back on epsilon B. So every transition now, I think, does exactly one of push or pop. Well, are we done yet? Well, we need a single final state with nothing coming out of it. Do we have that? Yeah. Technically, I should put another state because I want it to be algorithmic, but we already kind of have it here, so that's fine. But what else do we need? Well, we already have that. It's something to do with the final state. Yeah. We could, because of the construction, verify that it really is empty, but for algorithmic reasons, we need to put the self loops on Q8 to guarantee that the stack could be emptied. So here, we just need to be able to pop every character that could appear on the stack. Well, we push C and A on. Well, we also push the variables on. And we push the $sign on. But I think those are the only things that ever get put on the stack. Okay. Well, let's do one of each of the three rule types, let's say. So type 1. What is a rule of type 1? Yeah, so A sub Q0, Q0 makes empty. Same state to same state, one way that variable, one thing that variable could generate is the empty string. All right, cool. What about type 2? Just one example is fine. Good. So Q0, Q0, A, Q0, Q1. So for all choices of three states, some state to some state, you produce some variable, A sub first state, any other state. Then the second variable, the first one is the same as the second of the first variable. And then the one at the end is the same. So we just got to make sure that these match up, and those match up. But it doesn't look at the PDA whatsoever. Okay, type 3, the best one. So pick a pair of any transitions that are compatible. Any example? Q0 to QF. Q0 to Q1 where we push on the $sign. Q2 to Q8 because I pop off the same character. Okay, so that's fine. So I'm gonna redraw them here. So push dollar sign, and Q2, oh, this is Q1, sorry. Q2 to Q8, and that's pop dollar sign. And both of these transitions, as we can see in the diagram, don't read anything. So what should the rule be that I add? Yeah, yep, AQ0, Q8, the big problem I want to solve. What do I read on my way to Q1? Nothing, so I just wrote it. What's the subproblem? Q1 to Q2, right? AQ1, Q2. And to get from 2 to 8, what do I read? Nothing. So that's the rule. And you can actually kind of verify that to yourself. If I know how to get from 1 to 2, then that's the same strings that take me from 0 to 8. Because on both of those transitions, I don't read anything. Okay? Cool. Does that answer your question? Cool. Other questions? Yeah.
Can you do one from this PDA where you do actually?
Oh, sure. Sure. Any example of transitions where we read? You don't have to look too hard. Yeah, the two pop transitions on the self loop. Okay, so those are A and C. What other, pick any transition where it pushes an A or a C. Okay, Q5 to Q2, that pushes an A. Okay? So Q5 to Q2, so that pushes an A. And Q2, well, the thing that reads and pops the A is a self loop on Q2. But I'll depict it as a whole transition. What does the Q5 to Q2 transition read? Q5 to Q2. Nothing. Okay, so I should have, yeah. So this should be don't read. And what does Q2 to Q2 read that transition? Yeah, this reads an A. So what should my rule that I make be? Yep, AQ5, Q2 will make what? Well, on my way from 5 to 2, what do I read? Well, I don't read anything from 5 to 2, so epsilon goes there. What's the subproblem? AQ2, Q2, good. From my way from 2 to 2, what do I read? A. No, it's the thing that you read on the push transition, the subproblem, than what you read on the pop transition.
So the push would be in front. If it was something, it would be.
Yeah, the push would go in front if we read anything. Mm-hmm. Nice. Any questions about that? You do it for all pairs of transitions where one pushes a certain symbol and the other one pops the exact same symbol. Yeah, the reason why we add these at the very end, the self loops on the final state, is if considered any transition that reads and pushes some character, but no other transition otherwise pops that character, then we need to be able to relate that with the stack. And so therefore, we need to put those pop transitions at the end. Yeah, so it's with any transition that involves the stack where one pushes and the other one pops the exact same symbol, every pair. Mm-hmm. Other questions? Yeah.
On the Turing machine, it's not valid to not write anything. You have to write everything.
Well, we have that shorthand to say you're writing the exact same symbol, but in effect, you always are writing, as with the formal definition. You could think of Turing machines that don't write, but they effectively do the same thing. So, yeah. Yeah, they always write on every transition. Other questions? Mm-hmm. An example? Sorry, go ahead. Asking about infinite DFA or any of those related problems. Anyone have any example? Sorry?
Could we prove infinite PDA?
Yes, but it's a little harder. Yeah, the proof is almost exactly the same, but you have to worry a little bit about some other things, but it's almost exactly the same. It's an exercise in the book. So so why is infinite DFA decidable? Well, if it accepts any string at least a number of states in the DFA, then by the pumping lemma argument, you must have repeated a state. And then therefore, if you just repeat that loop as many times as you want, then you'll accept every single one of those strings. So if it accepts any string of length at least p, then your language is infinite. But suppose it doesn't accept any string of length at least p. Well, the longest string it could accept has length at most p minus 1. Well, how many strings are of length at most p minus 1? Some finite number. And so therefore, you can decide whether it has an infinite language or finite language. Yeah.
So we're going to be able to just use the them as encapsulated things, right?
Yeah, as black boxes, yeah. Anything we covered in class that's fair game to be used as black boxes.
You go into why. Just have to say this is
Well, if you use it in a non-trivial way, you should explain why you're using it that way. Yeah, but if it's like, it's not going to be this, but if I happen to ask finite DFA, determine if it's a finite language, then you just say run infinite DFA on the input and swap the answer. That's pretty obvious, but if it's anything like really non-trivial, you should say why. Yeah.
This question's actually about Chauncey normal form.
Okay.
From what I remember, don't you have to have S0 generates epsilon as a rule at
No.
some point?
You do not have to have it, but if you determine that S0, the new start variable, is nullable, then you will put that there.
But otherwise, don't put it there.
Of course, because if it's not nullable, it couldn't have made it. Yeah. Sure. How about let's do the exact same example we did. What's there? Yeah, yeah. All right. Well, and then I don't know if this is true, but prove that the language of this CFG is not regular. No, I think it is regular. So if I want to convert this thing to C and F, what should I do? A start variable. Yep. So step 1, make a new start variable. So how do I do that? Yeah, S0 is going to make S, where S0 is the new start variable. If that rule that has ASC and SA were not there, do I need to do that first step? I should do that first step, but do I need to as if I'm doing this in general? No, because there's no rule with the start variable on the right-hand side. Okay, step 2, what do I do? That actually rhymed. So what do I need to determine here? Nullable variables, okay. What are the nullable variables in this grammar? Yeah, so B makes epsilon directly. Is S nullable? Yeah, because it has a rule where every single variable on the right-hand side is nullable, which is B in this case. So I'm going to keep a list. Yep, for the exact same reason. S0 is also nullable. So what do I need to do once I know that information? Yeah, so I'm going to make that substitution for S0 right away because I know the epsilon is going to go there. But how do I simulate the epsilon rules in the other variables? Yeah, so I'm actually going to move this over here. So say for S to ASC, I know S is nullable. How do I simulate that there? Yeah, add a rule little ac. I shouldn't add the S to B one and make B drop out because it can't have an epsilon rule anyway. So I'm done with S. B, I'm gonna X the rule B to epsilon, but what else do I need to do? Yeah, make little a. Because S is nullable. Okay? Cool.
So Professor, you can put the B to epsilon because he's still gonna get rid of it, but we can just put it and then come back and get rid of epsilon.
I'm not sure what the question is, sorry.
So when you put, because B is nullable, you put a C and you took off the S. So you didn't do it for B, is it because you're still gonna come back to
Yeah, because I determined S is nullable. So S has a possibility of making the empty string in the grammar before, so therefore I make it go away.
Right, so is it wrong to say S goes to B and S also goes to epsilon and then come back and get rid of epsilon?
Well, you can't have S to epsilon because only the start variable can.
What about
S to, well, but I'm not going to do a look ahead. I don't do look ahead here. We do that in the where we eliminate unit roles.
Okay.
Yeah.
Sorry, I'm thinking.
Because since S is nullable, it could go away. So therefore, but it could make something else other than the empty string, so I keep the original rule and make S go away. Okay? Other questions? Okay, so what do I do next? Eliminate unit roles. Okay, how in the world am I going to do that? Well, what formally should I do? I should make a directed graph and have the edges of the directed graph be all of the unit roles. Yeah.
Is it incorrect if we do not show the direct graph on the bubble?
No.
Okay.
Yes. Like in this case, it actually turns out to be a DAG in this case because S0 goes to S and S goes to B and B goes nowhere. So formally, I should do this. And so what am I going to do here to fix the unit roles? Yeah, so let's start at B first. So what should I do? Yeah, so I'm gonna take the right-hand sides of B and put them in the right-hand side of S, where B was, because I'm gonna get rid of it. So put those there. And the exact same thing for the S part. Everything's in the way. I'm just gonna stick it on front. Okay. Should I delete B? I shouldn't for algorithmic reasons, but could I to make the grammar easier? Yes. So should you on the final exam? No. Good. Okay. Okay, there are no unit roles. Fine. What do I do now? Yeah, eliminate the mixture of variables and terminals, or too many terminals. Oh, I should say that this is step 3. So step 4 is, so how do we fix the mix of variables and terminals? Yeah, make new variables for all the terminals. Good. So,
Can I ask you a question before we start?
yeah, go ahead.
So like when we were learning this in class the very first time, you put like a new variable for every single A in each line, and you like.
No, that was for step 5.
But you made two like. Oh.
Yeah, that was for step 5 because I want only one way in to those 2 variables and one way out.
Okay.
Here, I don't need to. Well, I could reuse them in that step, but I'm not going to reuse them here because they only make one string, well, one character, and so therefore it's not going to go anywhere else in the grammar. So it's easier for correctness reasons too. So I'm going to replace these occurrences with use of A and use of C. Should I replace that single terminal on the right-hand side of S0?
No.
No, because then I will make a unit roll again, and I just eliminated those. So, but I should replace the one that has 2 terminals. And I'm going to make a simplification by just doing this, which you can do on the final. Because there's no point in rewriting those because it's exactly the same in this case. But I should put that. Okay. Any questions on that step? Are we in C and F yet? No. What do we need to fix? The long right-hand side's good. That was actually good grammar to start with. Quite amazing how lucky I get sometimes. All right, let's copy this guy down. So should I change any of the rules that have epsilon or single terminal or 2 variables only? No, because those are already fine. What about the other ones? Yeah, I need to change this guy right here because it has 3 variables. How did we fix that in class? Yeah, we'll make a new variable that, so it actually doesn't matter which ones you pick, but you might as well just pick the first 2, for example. So let's have this new variable make use of AS, and then replace it up here. And Y1. So I should make a brand new variable for the second time that occurs because I only want one way in and one way out. But the rest is the same because I'm not replacing any of it.
Well, we can still use Y1, right?
It's not wrong if I did that, but the way we verified correctness is that there was only one way in and one way out. So if I wanted to apply Y1, there's only one possible way that it could be applied, which was from S0. But it's not wrong if you reuse it. If you reuse it incorrectly, then it's wrong. But it's not wrong if you separate them like this or reuse the same one in the same places. Okay? Yeah.
Just out of my own curiosity, if you were to get rid of that S0 goes to epsilon, not in the case of Chauncey normal form, but you couldn't generate anything with that, correct?
No, you
You
could.
could still generate terminals.
Yeah. So if I axed this S0 to epsilon, then I changed the language, obviously. But I can still make exactly the same thing as before because the only way I could make epsilon is from the start variable directly. And I have no way of getting back to the start variable. So any rule that I apply here, each one of the variables is going to make something of the string. So it's not that I can't generate anything anymore, it's just I generate less.
Okay. See,
Yeah.
that's why I kind of was like always slapping on epsilon on that start variable.
Yeah.
That makes sense.
Yeah.
Okay.
if the original grammar was only the empty string and you had something like this and then you deleted it, then it won't generate anything.
Okay.
Yeah. Other questions about CNF? Okay. What else? Yeah. Oh boy. Trying to think of a good example that we didn't do. How about this one? So we went over this one in class, but it bears repeating. So,
But that's you already did that one though.
what's that?
It's exact same.
Yeah, but it bears repeating.
Okay.
Okay. So how would I show that this is not a CFL? Assume it is. All right. Then now what? Yeah, there exists a. Yep, there exists a P for L. All right. What now? Yes. Thank you. Yeah.
So this is a pretty easy example of finding string in the language.
Yeah, it's easy to find a string in the language that has at least P characters. Let me show you one that does have both properties, but tell me why I shouldn't pick this string. It has at least P characters and is in the language. But why should I not pick that string? Well, is there a decomposition that always stays in the language no matter how I pump it? Yeah, what is it? How about we called it U, be whatever, V be a single zero, X be the pound sign, Y be a single zero, and Z be the rest. Well, no matter how I pump, I'm going to put a zero on both sides of the pound sign in the same number every time. So it'll always be of the form W pound sign W. So I shouldn't pick that string. So bad, Ryan. That was a bad choice.
And the reason why is because that was the clause 3, right, for all.
Yeah, it says that there exists a decomposition such that no matter how you pump it, no matter how many times you put V and Y into the string, you stay in the language every time. Yeah. Yeah, so it says that the 3 middle parts are not too long, the 2 middle parts are non-empty together, and if you put in I copies of V and I copies of Y, so this I should say for all. If you put in I copies of V and I copies of Y, you always stay in the language. And the question is, does there exist a decomposition such that that condition holds? Well, the one I just described for this string, yeah, there is one that always stays in the language, no matter how we pump it, yeah.
So you can come up with your own decomposition types, right?
Yeah, for a given string, to show that you stay in the language. But to show that it's not context-free, you have to find a string such that no matter how you pump it, no matter how you decompose it, you can get out of the language for some value of I, because it violates the for all condition. Okay? So I better not pick that string. Should I pick 1 to the P, pound sign 1 to the P? No, effectively the same. So I gotta have a mix of zeros and ones on both sides. Examples.
0, P, 1, P, pound sign.
Yeah, that's a perfectly valid one. Because it's of the form W pound sign W. Okay, well, let's see. I gotta show for every decomposition. Should I show for one decomposition? Yes, I need to show every decomposition. Should I only show one though? Do I only need one? No, I need to show every decomposition.
We just show one now.
I guarantee you get 0 points on that question if you do. Okay, so every decomposition. Well, what do the decompositions possibly look like? Well, let's see. Well, yeah.
Why do you need to show every decomposition?
Because the pumping lemma says that there exists a decomposition such that no matter what value of I you pick, you stay in the language. But I want to show that once you start with this string, for every decomposition you pick, there is a way to get out of the language. It's complementing the statement.
Oh, so the statement, the pumping lemma was for all decompositions.
No, the pumping lemma statement says there exists a decomposition, such that for every value of I, you stay in the language. And then what we're trying to show is, starting with a string in the language, for every decomposition of this string, you can pump out. It's just a complement of the statement.
But if you found one that lets you pump out, and you would.
That doesn't imply anything, because some other decomposition might work. Yep, so we have to show every decomposition. Okay, well, what are some possible decompositions of this string according to those rules? Well, it could be all in the zeros, or all in the ones, or a mix of zeros and ones. Could it be some zeros and some zeros? No, because it has at most P characters. Okay? Well, let's make it a little easier on ourselves. What if all three parts, V, X, Y, were all before the pound sign? Could I pump out of the language and get something that's not of the form W pound sign W? Yeah, how would I do it? Just pump up once. Then will the first part's length be the same as the second part's length? No, why is that? Well, how many characters did I put in? Did I put in 0? I put in at least 1 character, because VY's length is at least 1. And those are the parts I'm putting in. So, case 1, if V, X, Y are, I guess is, before the pound sign, then pump up length of left-hand side not equal to length of right-hand side. Okay? What's another possible set of decompositions? Yeah, could it be all on the right side? Oh, how would I show that I can pump out? It's exactly the same strategy. Pump up, the length of the right-hand side is not equal to the thing on the left-hand side. So it can't be of the form W pound sign W. So it's almost exactly the same, but I just substitute after instead.
Would you have to pump on the pound sign?
We have to consider that, yeah.
How can VXY be after
The length of VXY is at most P, but we have these U and Z strings on the left and right side where we don't constrain their lengths. We only constrain the middle 3 parts. Yeah, so it can be anywhere in the string.
So the other ones can be empty?
You mean U, X, and Z? Yes, for sure. Yes. Okay. What are some other decompositions that may happen? What if either of the two parts, V or Y, what if either of them contain the pound sign? How would I get to something that's not in the language? Yeah, if I pump up, how many pound signs will I have? More than one, or at least two. Is that in the language? No. So that's enough. Could I pump down here? Yeah, if I pump down, then I'll have 0 of them, which is also not in the language. So V and Y, yeah. I should say V or Y contain the pound sign pump. Let's do down for this one, because we can change which direction we pump based on the case. Pump down, there will be 0 pound signs. And that's enough justification. Are all those all the possibility for decompositions? Right. What if V was in the first set of ones and Y was in the second set of zeros, but neither of them had the pound sign? Well, that's certainly a case. If V in first set of ones and Y in second set of zeros, could I get to something that is not in the language? Yeah, how would I do it? Yeah, what if I pump up or down? Both will work here. What if I pump up? Well, it could be that V is empty and Y isn't, right? All I said is that V or Y is not empty, or both. Well, whichever one is the case, I'm going to increase the number on one side at least. So let's see. If V happens to be non-empty, then I'm going to increase the number of ones on the left side, but will I increase them on the right side? No. What if Y was the empty one? I'm going to increase the number of zeros on the right side, but will I increase them on the left side? No. And those two reasons are because, right, it has at most P characters. Okay? So then pump up the jam. Because numbers of each character, I should not say each, I should say at least one character will not match. Yeah.
So if you were thinking of string, say for this,
Mhm.
you have to list all that out. And just say,
Yes. Yeah, you have to look at every decomposition.
So with the
Have I said that enough?
Okay. Okay. So just to clarify, the reason why the first one did not work is because so there is kind of decomposition that do work, but not
Yes.
because there was one that doesn't.
No, for the first one, there is a decomposition that allows us to always stay in the language. Whereas for the second one, there's no decomposition that works. As long as there's some decomposition that works, we're good. Mhm. Yeah.
So the way it's explained in the book, it doesn't even use a there exists condition. It just says literally, when there's going to be A, of which at least P, then S may be divided by P. So maybe means you have to show that it may not be what you're saying. But this is not even a there exists. It's not mathematical at all.
Okay. Mhm. Yeah, but there's it should say there is at least one. Yeah.
I'm using exists like
That there exists a decomposition means there's at least one.
It's
Mhm.
not like formally written. It's saying there may be decomposition viable in 5 cases.
Mm.
So you're showing there may not be.
Yeah, in the case of this string, because there's none.
Find every case. It's
Yep.
not possible.
Mhm. Other questions?
Can we give an example of case 1 when you say VXY should be everything before the pound sign? So VXY equals to 0 to the P, 1 to the P, and you say pump off, do you mean we should make it double?
No, I'm saying there are many possible decompositions of VXY into the first half. For example, if VXY were entirely in the zeros, or entirely in the ones, or a mix of both. I'm just saying, if it's all over on the left side, then we can pump out. So, like as an example. So like if we have a bunch of zeros, ones, and then maybe the V part is right here, the X part's here, and the Y part's here, for example. That's one decomposition. So it wouldn't work to say that VXY is equal to 0 to the P, 1 to the P, because it can't. Because that has length 2P, which is longer than P. So I'm just saying, for all decompositions that have VXY in the first half, then you can use this to pump out. For all ones in the second half, you can do that, yeah.
How do we pump out this act? So we can only increase.
Yeah, yeah. So if we pump up, we're adding another copy of V and Y into the string. Yeah. Yep.
Is this like the formal way you want us to write it?
Yeah. So with context-free, there are more cases to consider, and being a little informal is okay. For regular, it's often easier to do it formally. So, other questions? So what should you bring to the second half of Monday's class? Questions. Thank you. I mean, I could talk about why the sky is blue for a straight 60 minutes, but
You proved the question 2 part, I mean, question 1 from the midterm part B, the context-free languages, that was the one you answered.
yeah, sure.
You just worked through midterm too, right?
So let L over sigma star be a CFL, and H is a homomorphism from sigma star to gamma star. So all that means is you provide some string in sigma star to H, it spits out a string in gamma star. That's all it means. Okay? Well, let's see. How do I show that? So H of L is just the, if you apply the function H to every string in the language, then you get H of L by definition. That's the definition of H of L. Then, how do I show H of L is also context-free? Well, let's see. Well, if we know that L is a context-free language, what do we know otherwise? It has a PDA or it has a CFG. So PDAs will make this a little bit harder, but we can still do it. We'll work with CFGs for now. So we know that L has a CFG G. I just want to give the formal parts of it, but it's not going to be necessary here. Well, let's see. If I produce a terminal of G, right? What should I have produced if I want to have a grammar for H of L? Let's say I read the terminal A. What's that?
Isn't it 2 terminals?
But it's an arbitrary grammar.
Wasn't that the homomorphism though, where it makes two?
No. It takes an arbitrary string and it outputs some string in gamma star. Well, if I produce a single terminal in the original grammar, what should I have produced for h of L? The h of that terminal. So, to make a CFG for h of L, replace every occurrence of terminal A in G with h of A. And why does this produce h of L? Well, look at a derivation in the original grammar. And if you look at the exact same of a set of rules that were applied, you're looking at h of that particular string and the other way around. Yeah.
So homomorphism, this sense, in this example, actually, is just saying, well, I don't know, is homomorphism always in this like arena doing the same thing to like the grammar or doing like the language?
Yeah, no, we're defining it to be that way. Yeah.
Because homomorphism usually is, we do the same thing.
Yeah, yeah. So h of L, that is a definition of a language name. That's not a function. But h of W, that is a function. So it's unfortunate naming, but yeah, you have to make sacrifices sometime. So let's actually do an example because many people ask me about this. So let's, don't know how much time we have. So let's, again, look at the same grammar. And let's consider h of A is the string $$, and h of C is smiley face. No. Let's be fun with this. $, smiley face, $. Well, it's a valid alphabet and it's a function from the original set of terminals to some string in the resulting output alphabet. So what should I have for the grammar be it right now? If I want to have the one for the homomorphism of whatever language this is. Yeah, so replace every terminal with its corresponding homomorphism. So $, S, $, smiley face, $, or B. B produces epsilon, or S, $, $. Yeah. Yeah. What in the hell are they teaching in that class? But we're at a university, folks. We talk about $signs and smiley faces. All right. Yeah, but is the idea of homomorphism clear? Yeah, all you're doing is for every terminal, replace it with the string. Well, could we do the same thing for PDAs? Well, we could try, but the problem is I can't have a string on a single transition. So what do? Break up the resulting h of whatever string into single character parts, and then make a new transition for each. Okay, but it works exactly the same way. Other questions? We have like 1 minute. But then office hours, but yeah. Oh, what do you mean, what do we do? I just did an example of what homomorphism actually means. Yeah, because some people were confused.
So that's enough to prove it in general to make a CFG of HL.
Yeah, we should save the correctness reasons because if you look at a derivation in the original grammar, do you have one in the resulting grammar and vice versa?
I see. So both ways.
Yeah. Yeah, but it seems pretty obvious because if you look at a derivation, then look at the same set of rules applied, you are looking at h of w. Because the homomorphism is just the homomorphism of the single character repeated. Yeah. Other questions? All right, let's take a break.